Now we're diving into the heart of a single pipeline ADC stage, the switch-capacitor multiplying digital-to-analog converter, or MDAC. This circuit is a real workhorse. Its job is to calculate the residue, that is, the small leftover part of the signal that the stage's sub-ADC couldn't quite resolve, and then amplify it for the next stage in the pipeline. Let's look at the components. For an M-bit stage, this circuit uses an array of 2 to the power of m unit capacitors. So, as the note at the bottom says, if we were building a 4-bit stage, like the 4-bit flash ADC we just saw, m would be 4 and we'd need 2 to the power of 4, which is 16 of these unit capacitors. It also has a feedback capacitor, CF, an op-amp, and a bunch of switches. The whole operation is controlled by 2 non-overlapping clock signals, phi1 and phi2, which you can see at the bottom left. The process happens in 2 distinct steps, or phases, dictated by these clocks. First is the sample or reset phase, which happens when the phi1 clock signal is high. During this time, the circuit does exactly what the name implies. It samples the input. The input voltage, VIN, is connected to the capacitor array, and a certain amount of charge, proportional to VIN, is stored on these capacitors. At the same time, the op-amp is put into a reset configuration to ensure it starts from a known, stable state for the next phase. So, think of phase 1 as the get-ready phase. It captures the input and resets the circuit. The real magic happens in the second phase, the amplification phase, when phi2 goes high. 3 critical things happen here, almost simultaneously. First, there's a digital-to-analog conversion, the DAC part of MDAC. The digital output code from this stage's sub-ADC controls the switches connected to the capacitor array. Based on this code, the capacitors are connected to a positive or negative reference voltage. This effectively converts the digital code back into a precise analog voltage. Second is subtraction. The circuit is designed so that this newly created analog voltage is subtracted from the original input voltage that was sampled in phase 1. The result of this subtraction is the quantization error, or what we call the residue. It's the difference between the actual input and the closest value the sub-ADC could represent. Finally, we have amplification, which is also the multiplying part. This residue voltage is typically very small. To make it useful for the next stage in the pipeline, we need to make it bigger. The op-amp, along with the ratio of the sampling capacitors to the feedback capacitor, CF, amplifies this residue, scaling it up to fill the full input range of the next stage. This is a crucial step because it means the later stages in the pipeline don't have to be nearly as precise as the first one, which saves a lot of power and complexity. So, to summarize, the MDAC takes the input voltage and the digital decision from the sub-ADC. In 2 clock phases, it performs a DAC, a subtraction, and an amplification to generate an amplified error signal or residue, which it then passes down the line for the next stage to process. Following up on the 2 phases of the switch-capacitor MDAC, let's now dive into the mathematics to understand exactly how it calculates the residue voltage. It all comes down to a fundamental principle in physics, the conservation of charge. First, let's look at the sample phase, when clock phi is high. During this time, the input voltage VIN is being sampled onto the array of input capacitors, which are labeled C through C2-M. The total amount of charge stored across all these capacitors is what we call QS. As the first formula on the page shows, this is simply the sum of the charges on each individual capacitor. Since the charge on a capacitor is its capacitance times the voltage across it, Q equals CV. The total sampled charge QS is the sum of CI times VIN for all the input capacitors. Think of this step as capturing a snapshot of the input voltage and storing it as an amount of electrical charge. Now, things get interesting in the amplification phase, when phi2 is high. The input is disconnected, and the circuit reconfigures. The charge stored during this phase at the op-amp's input node is called QA. This charge now comes from 2 places. First, the input capacitors CI are now connected to a reference voltage, plus VR or VR, based on the digital decision T made by the sub-ADC in the previous step. This is the digital to analog conversion part. We're converting the digital bits T back into an analog charge. Second, the feedback capacitor CF is now connected around the op-amp, and it holds a charge determined by the output residue voltage, VRES. So, as the second formula shows, QA is the sum of the charge from the reference voltages plus the charge on the feedback capacitor. The magic happens because the inverting input of the op-amp is an isolated node. No charge can enter or leave it. This means the total charge must be conserved between the two phases. So, the sampled charge QS from the first phase must be equal to the charge QA in the second phase. By setting QS equal to QA and rearranging the equation to solve for VRES, we get the final expression for the residue voltage. Let's break down that equation. The numerator has two parts. The first part is the total charge from the input signal that we sampled initially. The second part is the amount of charge that we subtract, which is determined by the digital output of the sub-ADC. This is the core subtraction function of the MDAC. The result of this subtraction, the leftover or residue charge, is then divided by the feedback capacitance CF. This division by CF is what amplifies the residue, scaling it up for the next stage in the pipeline. Finally, the slide touches on the gain of this MDAC stage. The gain is essentially the ratio of the total input capacitance to the feedback capacitance. If we make the feedback capacitor CF equal to the unit input capacitor CI, the gain is approximately 2 M. However, if we make CF twice as large as CI, the gain is halved to about 2 M. Why would we want to change the gain? Well, a lower gain can make the circuit more tolerant to errors like comparator. Offsets, a very important concept that we'll be exploring in detail very soon.